Huh, I wonder what this is.
I can answer your question. What you're holding there is a piece of zircon, a tetragonal mineral found all over the world, from the outback of Australia all the way to the frigid Soviet Union.
The Soviet Union doesn't even exist anymore.
What just happened? How did we get here? And what happened to my clothes? Did you comb my hair? And why are we in black and white?
Another great question, Billy.
Not my
Zircon, with chemical formula ZrSiO4, has been known since the time of antiquity, but the origin of the name is unknown. Zircon forms metamorphic rocks, igneous rocks, and can sometimes be found in detrital sediments.
So zircon can be found just about anywhere in the world.
That's right, Davey. Zircon can be found on all 7 continents, in even more places than Sputnik can spy on.
Sputnik was a satellite. So you said that zircon is a tetragonal mineral. That means all of its angles have to be equal to 90 degrees. And not all of its sides are equal. A equals B, but does not equal C. Well, so what does zircon look like?
Well, Johnny, zircon can have a greasy, vitreous, or even adamantine luster. Not only that, it has a white streak to boot. As for the colors, though, it comes in colorless, white, yellow, green, blue, grayish brown, pink, reddish brown, and Moscow's favorite, red.
Huh, now I remember zircon. But putting aside the red scare for a moment, doesn't zircon have a 7.5 on the Mohs hardness scale? And I believe it's got a imperfect cleavage in one direction, and it fractures conchoidally. But what about its optical properties?
Well, Jimmy, you'd be just right with those observations. As a tetragonal mineral, its optical class is uniaxial, and it has a very high refractive index of just about 1.9 to slightly over 2.0.
Wow, I bet it has a weak pleoprism, too.
Right again, Scotty.
Not the name.
Its maximum birefringence value is about 0.055, and not only that, but it's a fluorescent mineral, it's thermoluminescent, and it's cathodoluminescent.
Wow.
Gee Willikers is right.
Where are we?
Never mind that, Stevie. What can you tell me about the shape and habit of zircon?
Well, I think it's prismatic to bipyramidal.
There you go. And the Miller indices?
If I'm correct, they should be on the planes of 100, 301, and 101.
You would be exactly correct, Davey.
Stop it! You just moved us like 10 feet.
Never mind that, Lucy. The more important thing are to look at some similar minerals to zircon, namely vesuvianite and cassiterite, which are softer and heavier, respectively.
Okay, seriously, you have to stop doing that.
But Davey, zircons can be found all over the world.
Well, that is true. It can be found in France. No, that's central Canada. There's France. Pakistan. That's the South Pacific. Just run into that. Pakistan. Finland. Let me think. Vietnam. Canada. Oh, and most importantly, Australia.
As a matter of fact, the oldest zircons in the world were found in the Jack Hills region of Western Australia.
Isn't that right around here?
Yep, it's right in that area. In fact, they were 4.404 billion years old.
See, off the top of my head, that's about 97% of the Earth's history.
Spot on, Scotty.
But how do they know they're that old?
The primary way that we can tell the age of a zircon crystal is through a process with radiometric dating called uranium-lead dating.
So the reason that zircon sticks around for so long, though, must be that it's chemically inert. It's really durable and hard to destroy. I bet the only place it can be destroyed is in subduction zones.
Correct again. And the reason that we can do this with uranium is because uranium has the capability to substitute in for zircon in a crystal. So rather than ZrSiO4, you now have a USiO4.
Oh.
Uranium-235 can decay through a process of 6 alpha decays where it essentially spits out a helium nucleus to lead-207. Now, the half-life on that process is about 700 million years. The other process that can be found in this is a different isotope, uranium-238, decaying through a 7-alpha decay process to lead-206. This one takes even longer, with a half-life of about 4.47 billion years. Now, we can take this and plug it into an equation for radioactive decay here, and we'll see that the number of daughter isotopes left in the sample will be equal to the number of daughter isotopes originally, in that case being lead, times or plus the number of uranium atoms and some function of the half-life and time.
Well, that's all well and good, but how do we know the initial number of lead atoms in the sample?
Well, that's an easy one, Jackie. We know that while uranium can easily substitute into zircon, it's actually very effective at blocking lead, so the initial concentration is none. There's just not any there.
So, what are the limitations on this process?
Really, the only limitation is the lead retention temperature of zircon, which is about 900 degrees Celsius, so even at that, it's not much of a problem. The age range that can be covered with uranium-lead dating spans from about 1 million years to over 4.5 billion years. Not only can it cover such a big range, it can do it with a precision regularly of 0.1 to 1%.
Wow. So, zircon dating is really important in understanding the history of the Earth.
It's true, because the mineral is so ubiquitous around the crust, it's very easy to see it and to date the creation of different areas and the movements of line patterns.
Golly!
Gee willikers.
So, are there any other common uses for the mineral zircon?
Well, funny you should ask. In fact, there are some. When people confuse high-quality zircon crystals, they sometimes begin to think that they're precious gems. Sometimes being known fake diamonds made of zircon actually being called Matara diamonds. Not only that, but because of the toughness of the crystals, they're lots of times used in industrial cutting devices.
Wow, that's really interesting. Hello? Dr. I guess I don't know your name. Dr. Geode? Alright, well, I'm just gonna head out then. Alright, I'm going.